In this fifth lecture, we're going to look at the detection of the signal in an electron microscope. But before we embark on this new topic, let's first look at what we have treated so far. So the key concepts are, of course, the concept of scanning in an electron microscope, the different contributions to the probe size or the resolution of the electron microscope. We've looked at the different types of sources and their key characteristics. We have learned what brightness is and how it relates to current, and we have looked at the role of energy spread in the beam. We also looked at the different concepts for lenses, specifically magnetic lenses, and we looked at the considerations we have for putting samples in electron microscope and shielding the electron microscope room because of the fact that we use magnetic fields. And we've also learned that we can have samples immersed in the magnetic field. We also briefly summarized the basic SEM concept and the microscope layout, including the use of apertures to limit current and beam angles. And we looked at the relation between the numerical aperture and the focal depth, seeing that in an electron microscope we can have a relatively large focal depth. Finally, we have briefly looked at what astigmatism is and why it is important in an electron microscope. So basically what we've done in the previous lecture is understand all the concepts to get an electron beam in vacuum and focus it onto the sample. Now we have it focused on the sample, then what happens? We know from the lecture about electron-matter interactions that we have scattering, elastic events, inelastic events. This leads to the occurrence of scattered electrons. If we have a thin sample, transmitted electrons, it can lead to the emission of visible light or even of X-rays. Now all these different events can constitute a signal that we can detect, and this will be the subject of today's lecture. So what we will look at today is how to detect these signals, and specifically the secondary electron signal, so resulting from inelastic collisions, and the backscattered electron signal relating from the elastic collisions. We will look at what type of contrast these different signals gives, or the imaging modes that we have in an electron microscope. We will also briefly touch upon the vacuum in the electron microscope and the current we put on a sample, which can lead to charging of the sample. And at the end of this lecture, we will look at the preparation of a sample for electron microscope, because the sample has to go in vacuum and we have to prevent it from getting charging, while at the same time we want to look at a biological specimen that is in a state as native as possible, which is very much conflicting requirements. So let's look again at the schematic view of scattering that we have seen in the third lecture. So you see that depicted here, an atomic nucleus with a cloud of electrons, giving rise to a potential around the nucleus, and to the right a depiction of the nucleus itself with electrons orbiting the nucleus. Now we have the incoming electrons depicted in yellow. They can be transmitted if they travel the space without being affected by the potential field of nucleus or surrounding electrons. They can be attracted by the positive electrostatic force of the nucleus, leading to a comet-like trajectory of the electron, giving rise to backscattering. Of course, it can also be scattered in the forward direction, contributing also to the transmitted electron signal. And we can have the incoming electron interacting with the orbiting electrons surrounding the nucleus, kicking an electron out of its energy level, leading to the emission of secondary electrons, lower energy electrons, or when this leaves a hole, we can look at the X-rays that are generated when a higher energy electron falls back into this hole left by the exited electron. Now you see in this graph here depicted the typical energy spectrum of the emitted electrons. So on the horizontal axis you see the energy of electrons emitted from the sample. E0 indicates the primary electron beam energy. So for a scanning electron microscope, this is typically on the order of 1 to 30 kilo electron volt. On the vertical axis, you see the number of electrons detected at a specific energy. So first, we see a huge peak at very low energies, typically below 50 electron volt with a maximum around 10 electron volt. So these are the secondary electrons, very low energy electrons. Then we see a very broad continuum with a small amount of minor peaks, which are the Auger electrons, which we will ignore in this lecture series. And then in the end, we get a few peaks and a final peak at E0, which is the primary beam energy and the backscattered electrons. Note that the peak at the low energies is very high, so relatively large amount of secondary electrons are generated, but the energy range here of course is small. While in the broad continuum, the density of electrons emitted may be low in terms of per energy, but of course it's a very large energy band, so these can still be a considerable number of electrons. Now everything below 50 electron volt we typically denote as secondary electrons. Everything above 50 electron volt up to the primary electron beam energy we denote as backscattered electrons. This is a bit arbitrary. It's good to remember that the secondary electrons energy typically is around 10 electron volt. The backscatter electron energy is typically close to the primary beam energy. Okay, we're going to first look at the secondary electrons. Now the secondary electrons have a very small energy, which means that they are very prone to interaction in the material in which they travel. So they can be generated deeper into the material depending on the penetration depth of the electron beam. But because of this finite travel length, they can only escape from a volume which is very close to the surface of this sample. You see that indicated in the image here to the right. So the drop-like shape you see is the approximate electron interaction volume, while the more stronger dashed area is the more stronger dashed volume is the volume from which the secondary electrons can actually escape from the sample. Now the important thing to realize for these secondary electrons is that when we would have a relief structure on the sample, as indicated to the left in this image, a larger fraction of the interaction volume may be exposed to the outer surface. This means that more secondary electrons may escape from an inclined surface than from a flat surface or from a trench. And this actually provides the dominant mechanism for the secondary electron contrast that we see if we detect these electrons in an electron microscope. Secondary electrons provide topography contrast. It's also what we already saw in the bug feature that we've seen before. So we very nicely see the outer surface of the animal with clear contrast coming from relief structures on its surface. I will now show you a small simulation which illustrates the effect of topography on the generation of secondary electron contrast. So in the image here you see in orange the simulated surface. We collect in this simulation all electrons exiting from the sample hitting a detector plane. This is an artificial detector plane which is indicated in yellow. Then in red we have our electron beam with a finite diameter hitting our sample and then undergoing scattering events. These scattering events are simulated in a Monte Carlo-like fashion. The electrons are traced after these scattering events. They can undergo multiple scattering events in the sample, and these scattering events are denoted in blue with a scale ranging to red if there's more events going on. We also see already in this image that several electrons escape the sample, indicated by straight path towards the detector plane or towards the orange surface relief structure next to the one where the electrons hit the sample. Now I will start the simulation. You will see the electron beam going over the sample. You will see that a different fraction of the interaction volume gets exposed to the outer surface, and above the detector plane you see the total amounts of electrons collected on this plane depicted in a curve. So the detected intensity. You see that once we hit the inclination surface, the signal increases. Well, if we are in the trench, it decreases because a large fraction of secondary electrons gets absorbed by the higher up surface. In the middle of the trench, it again increases because more electrons are free to escape. And if we hit the second surface, again the signal increases. Now how to detect these low energy electrons? So typically for this we use a detector that is called the Everhard-Thornley detector. The detector you see depicted in the image to the right here, and it's schematically indicated to the left. Note that these two images are inverted with respect to each other. So on the image you see a long tube with at the outer end, the left end, a grid-like structure. On this grid-like structure an electric field, electric potential is applied which sucks in the low energy electrons. Note that the electrons have a low energy, so they have a low velocity. So if we apply a voltage, say 250 volts, we can easily attract the electrons to this grid. You see that indicated in the image. If you look at the sample beam with an electron beam in black coming in, and you see the secondary electron trajectories going out and then being curved towards the dotted grid on top of the detector. Now, once the electrons pass this dotted grid, they are accelerated to an energy of typically a few kiloelectron volt, after which they hit a scintillator, are converted to visible light. This visible light is guided out, then again converted to an electric signal, which records the intensity for the specific position of the beam that we are examining at that point. Of course, after this we're going to scan the beam, so we're going to move to the next pixel, again the intensity is recorded, and so on, similar to how you saw it in the simulation that I ran before.